This is an interesting photograph.
Yes, you showed us this one.
Did we look at this last week?
Yeah, but in the context of the Boulder fields, not
right.
Oh, okay. So well, now we'll throw in Jeremy.
Yeah.
He's out there, leaping over the rocks. What we need is videos of Jeremy, because you can't get. He was very great, tall, kind of graceful, and he was a good runner, and he had a long stride. And but yeah, he's we're checking out the Hickory Run Boulder Field, composed of redstone, sandstones, and conglomerates. Very interesting. And then this one is the Blue Rocks Boulder Field in Pennsylvania. And so there we see Jeremy again. So these were two completely different trips here, or was it? With two completely different days, two completely different sites. And, Boulder fields are always interesting because their origins are not fully explained. At least the efforts to explain the origins of boulder fields using strictly gradualist or uniformitarian explanations never quite held up.
It doesn't really work.
And it's interesting because there's a stream that flows through here, but you don't see it because you can hear it.
It's under all the rocks.
Yeah, I would say those rocks are probably, it's a layer maybe 20 feet thick.
Wow.
But yeah, it's quite large. And as we talked about last time, it's the trees are slowly encroaching upon it.
Right.
And as the trees encroach upon it, they will be shedding their leaves. And then over many generations, those leaves will fill in all of the voids and spaces. And eventually the whole boulder field will be buried. More trees will grow there. You'll walk through the forest and not even know that this thing is under your feet. But see, when you walk into the forest from here, you begin to see exactly the process, because you can actually, it's almost time transgressive. You can see from bare rock, like you see here, and then as you go into the trees, the further away you get, the more progressively they get buried.
Yeah,
makes sense.
Little transition zone,
transition zone, exactly.
Where the encroaching is happening.
Yep,
that's really cool. I like to see that.
Yeah, and we're going to get into
deep
this
in the archives. There's some video.
Yeah, check this out. This is the Hickory Run.
Wow.
Now, and what's interesting to see here is because it's such a
those
flat
are more rounded.
surface.
Yeah, those are much more rounded than those other ones.
Yes, which is an indication of transport distance.
And all this is all the same type of rock?
No, this is the Hickory Run is a sandstone. Let's see. Redstone.
But each of these beds is essentially the same type of rock?
No, this is one type of rock.
Well, that's what I'm saying. They're two different fields with two different types of rock.
Two different types of rock.
But within each field, it's homogeneous.
Yes, that's right. Yeah. So these are two examples of what are called boulder fields and or boulder streams. Whether it's a boulder stream or a boulder field depends on width to length ratio of the feature.
What's the source of these?
Well, it's in the uplands. They were washed, I would think. I mean, I don't know how else you're going to transport them other than, if you have a very.
But I understand that. But where have they found the source for these?
Yeah. I mean, within not too many miles away, there are Appalachian mountains. So if you have a mass wasting event, it's the only thing that makes sense. I mean, like when you read the studies on them, they're scratching their heads trying to figure out the exact mechanism. I mean, they know where it came from, but how do you get it from point A to point B and spread it out on a flat surface? Okay, so here in the Blue Ridge, let's see, this is the quartzite. Yeah, so bare stream-like accumulations of boulders along valley bottoms occur at widely separated localities along the Blue Ridge from southern Pennsylvania to West Virginia. The boulders are loosely packed, unsorted, heterogeneous in size and shape, and range up to 12 feet in length. The sound of running water beneath the surface is audible. And in fact, in that picture right here of Jeremy, he's actually standing in that picture, listening to the running water. But that running water had nothing to do with the emplacement of this boulder field. Okay, so here we go. Here we go, Mike. Here's the answer to the question. The boulders are of quartzite derived from neighboring slopes and ridges. They are now lichen covered, are undergoing disintegration in place, and show no evidence of appreciable present day movement. The rock streams appear to be fossil forms and are best explained as a product of solifluction under paraglacial conditions in Pleistocene time. Solifluction is a type of mass wasting or mass movement. Kyle will look that up, SOLI, solifluctions, and it'll give us a little more precise definition that I would give you at the time. So let's hear what that says. Paraglacial simply means near the glaciers. So the idea here is you've got an environment that's not covered in glaciers, but the glaciers aren't far away. That's paraglacial, right? So they're best explained as a product of solifluction under paraglacial conditions in Pleistocene time with subsequent removal of interstitial material by running water. This explanation applies also to the boulder-choked valleys and subdued, overgrown talus slopes, which are more widespread in the area. So that's just what I was talking about. There are lots of these things around, but because, as it says there, they're overgrown. So because they're overgrown, people aren't aware of them, that a lot of this stuff is underfoot. And that's a big part of, trying to teach people this stuff, is because a lot of the evidence is obscured now. But it's all around us. And in this case, you might be walking on a trail in the forest and not understand the nature of the landscape under your feet. And what'd you find for solifluction there, Kyle?
It says the gradual movement of wet soil or other material down a slope, especially where frozen subsoil acts as a barrier to the percolation of water.
There we go. So frozen subsoil allows this saturation. But then if it melts, say it gets warm enough, then it becomes fluidized. So you got a picture. It's really almost like a slow mud flow, right? Although in this case, I would argue that it's not really actual solifluction the way you described it, because I would say the emplacement was much more rapid.
Right.
And one of the things that might have been going on is that during the deglaciation, you not only have the rapid saturation of the soil, right? You've got to somehow see, here's part of the problem. It's one thing to saturate the soil, but how do you get it loaded with these millions of boulders?
Yeah, it says it's a relatively rapid process in paraglacial regions and can result in the active development of slopes.
Yeah, and you know what? That interpretation of it there probably stems directly from the study of boulder fields, like we're looking at here. But so see, then this explanation applies also to the boulder-choked valleys and subdued, overgrown talus slopes, which are more widespread in the area. And then the previous sentence, subsequent removal of interstitial material. So picture you've got a mud flow, a very fluidized mud flow, choked with all of these boulders, right? Spreading out onto the valley floor from the adjacent uplands and ridges and slopes, spreads out. Okay, so now it's emplaced. Once that event is over, because this event was on a scale beyond what would normally be effective erosion or deposition in that particular area. So because of the scale and magnitude of it, once it's over, it's pretty much left in place. So now the running water, what it does, it doesn't really move the boulders, but it begins to wash out the material, the mud that these boulders would have been encased within. Does that make sense? And particularly if you have storms, so you have a lot of extra runoff, it's going to wash the mud out. But you're looking here basically at two very distinct regimes of deposition and erosion. The erosion that would wash away, the fine-grained soil from between the rocks is a whole different order of magnitude than the depositional event that put those rocks there in the first place. Does that make sense?
Yeah, it does.
Yeah.
Have you seen, I don't want to get too far off the main topic here, but have you seen Black Mountain in Australia? That's actually a pile of boulders. A mountain-sized pile. of gigantic boulders. And I've always wondered what geological process could have formed. Maybe we can look at that sometime.
Sure.
Yeah, I thought of the same thing the last time we were looking at the boulder fields.
It's literally a mountain
Hmm.
made of boulders, of gigantic black rocks.
So you got to, first of all, in a case like this, try to begin to, if you're going to try to explain the whole process, you got to
Yeah.
explain, okay, how do you get so many pieces of broken rock?
Right. Yep.
What's the story there? You get all of these pieces of broken rock, millions. And then he goes on.
That's the first question I would ask. What broke the rock up? Where does the broken rock come from?
Well, this particular geologist, in the conclusion of his paper, says that the tumultuous appearance, and if you look at it, it's not moving, but it still has what he's describing as a tumultuous appearance of the surface suggests, and this is a key phrase right here, arrested motion after forcible movement, somewhat in the fashion of an ice jam in a river. So you've got this process. It's a forcible movement in placing, somehow extracting these boulders from the ridge tops and the slopes, transporting, conveying them down onto the valley floor, and then spreading them out on the flat valley floor, so that the whole valley floor is basically mantled with these rocks that came down. So it seems, one, you need saturation. But is the saturation going to be enough to supercharge this matrix of muddy material with all of these broken rocks? So I think with Mike, the question is how do you break up all these thousands upon thousands of rocks in the first place? And I would suggest that the saturation is being accompanied by perhaps seismic events in the region, most likely due to deglaciation, which is also related to why you're having this super saturated soil in the area. And one of the things interesting about the Hickory Run is, like, you'll notice here that as you go from the top end of the flow to the bottom end, the rocks, this is the top end of the flow. Look at how sharp and jagged the rocks are here compared to when you get a couple of, 300-400 yards farther down. All right. So here's the upper end of the boulder field, and there's further down, maybe 300-400 yards farther down. And as you get to the lower end, you see that the rocks are rounder and smoother.
Yes.
And so I think right there, that's, direct indication of transport, and could also be used as a so-called paleo current indicator, because in this case, the current was going to be flowing from, obviously, if you've got this depositional layer there, and you have evidence that this layer was not transported as far as this layer, it would suggest that the flow is, from the sharp angular rocks towards the more rounded rocks.
Yeah.
Because they got transported farther. So with that kind of evidence, you can determine which way the flow was.
I would be interested to know also, I wonder if it's possible to figure this out, like how fast is the boundary of trees encroaching? And could you then, reverse engineer that and figure out how long it would take for this boulder field to be completely covered? And then maybe you could use that as an estimate for how old it is.
Well, yes. And in fact, if we go on here this is something I wanted to be covering soon anyway.
Okay.
But like here, this is Appalachian mountains and plateaus, vast areas covered by bouldery, generally unsorted and unstratified debris, lie along mountain foot slopes in many parts of the Blue Ridge. The origin of these foot slope deposits has been considered problematic. Study of modern debris slides in this region, however, makes these deposits somewhat more understandable. But then when we look at the next slide here, now this is typical. Of course, they're much smaller, which would imply a less vigorous flow of smaller magnitude than what emplaced either the Blue Rocks or Ringing Rocks in the Hickory Run boulder fields. But this is very, very typical of the stream bottoms of all throughout the Appalachians, right? Now, if you go, here's where this is the Pigeon River flowing through it. It's at the foot of Cold Mountain, the fairly famous Cold Mountain that the novel and the book was written around, the Civil War epic. Anatomy of a valley floor. Boulder cobble layer is superimposed on a scoured bedrock floor, and there's an immature soil horizon capping the boulder bed. And let's see, I should have, right here, scoured bedrock here. There we go. So that's actually bedrock right there. So it gives you an idea of the thickness of this boulder cobble layer. It's about 4 or 5 feet thick, and it's splayed out over a bedrock floor, right? If we look at the next one here, you can see for scale, actually, there's Jeremy again.
There's Jeremy.
We're out there collecting rocks for his rock shaping craft. That's what we're actually doing there. But I'm also, checking out the geology. So we have right here an exposed bedrock of a metamorphosed gneiss, right? So you got to picture this. This whole entire valley floor is mantled with this 5, 6, 7, 8 foot layer of cobbles and gravel and boulders.
And it's a scoured bedrock, which means something washed whatever was there away and replaced it with this cobble.
Mike got it, nailed it. Right. That's exactly right, Mike. Okay. So right there, Mike, you've justified your existence for at least another 2 or 3 episodes. Excellent insight, Mike. Yes, that was what I was going to see. I was going to see if Kyle actually was putting that together. But you beat.
I was just thinking of the word nice.
Nice.
So right there, you see that arrow that's pointing. That's a metamorphosed gneiss, and that is the bedrock, right? So you've got this layer, just like Mike said. You had to have a scoured surface first that exposed the bedrock, and then you had to have the deposition of the cobble, boulder, gravel layer. And then you have topsoil forming on that. Now, let's see if we have here. If you look, you'll see over here on the left, you'll see this layer of topsoil. It's about a foot thick. Well, I did some research in this environment of Western North Carolina under normal gradualistic circumstances. You can assume about a 1-inch thick layer of topsoil every 1,000 years. So
let me guess, it's 12 inches thick.
It's about a foot, maybe 16
there
inches.
You go.
In place. Yeah,
Mike's nailing it. On fire tonight, Mike.
He is the man is on fire. He is. I mean, look, I've seen this before in Mike. So check out over here on the right. You'll see that you've got this. The topsoil is very distinct from the underlying cobbles. And if we went over to the tree line and started digging down, we would find the same valley floor. And in fact, I would say that there was a time, if we had a time machine and we could go back 12 or 13,000 years to the right day, the right month or so, time of year, whatever, the right year, what we would see is a vast valley floor just basically covered in this stuff right here. And what the whole floor would look like is what you kind of are seeing right here. You get it? So
yeah.
How do you get that as the end result without having some kind of a extreme erosional event followed by an extreme depositional event? And then once those are over, not much happens because now it's a fossil feature. So in other words, the whole valley floor here is a fossil.
Yeah.
And you say this is predominant pretty much in Western North Carolina up along the Appalachians?
Oh, yeah. Oh, yeah. Absolutely it is.
I mean, we have this here too.
Yeah.
Kyle and I've noticed we've walked many stream beds, and there's a little bitty creek, but there's this enormous cobble / boulder field all around it.
Yep.
And then you can see farther up, you start to get thin topsoil.
Right.
And it's become clear to us looking at that stuff now. And you can also find places like that where you're pointing out where the exposed bedrock is, and it's clearly it's limestone in our case, and it's clearly been scoured by water.
Right.
Right. So yeah, it's become clear to us that a lot of water moved through these areas.
Yes.
Very quickly, carrying a whole bunch of crap that they later dropped.
You got to
After-
what you actually have to understand is what you're seeing here is the aftermath of highly erosive floods, flushing these valleys out, scouring right down to the bare bedrock. So whatever was there before is now gone.
Yeah.
Then as the floods decline, the same flowing water that scoured the valley floor now drops its cargo of huge amounts of broken rock that's being rolled and transported in this flood, mantles the valley floor with it. It's over, and now it sits there for 10, 12, 13,000, 14,000 years, whatever the length of time.
Right.
And the normal processes come in and slowly begin to conceal it. See, that's the thing, is that the modern processes are slowly destroying these fossil features, but so slowly that, after 10 or 12 or 15,000 years, they're still here. Now, how many people do you think will drive through this valley, see this, and never even have the slightest thought of what the story that's being told here by what you see?
Right.
Probably just about nobody. Interestingly, the time...
Everyone who watches this show. Everyone who watches this show.
Well, everyone who watches this show, yes.
That's what I'm saying. That's what this show is for, is to teach people how to be able to drive through valleys like this and see the thousands of years of geological story in these features.
Creating a context so they can recognize it, right?
Right. So, again, this would be going back to our little metaphor of fingerprints and footprints. This is kind of a footprint, although it's not an obvious one. It's not like a meteor crater or an extinct cataract. But, of course, a lot of people might look at an extinct cataract and not know it's an extinct cataract. See, we have extinct cataracts all over the southern Appalachians. But, they're generally so overgrown, and most people it's just a big amphitheater with a little waterfall going over it. And the amphitheater is 100 times bigger than the modern waterfall. Who stops to think about the fact that the amphitheater was originally created by a flow that might have been 100 or 1,000 times greater than the modern floods that are running through that particular valley?
Yeah.
10,
but that's what we're looking at here. So then this was another study. Now I was studying all this. This goes back to the 80s. So me and Jeremy are out there studying this stuff in the 80s and going out and I met Jeremy in 89, I think. So this is 89, 90, 91, 92 right there. But a lot of the studies that I had already been looking into, I'd already done some of the studies. So that's how I knew, okay, we're going to go up here to Cold Mountain, and I know that there's bedrock gneiss up there, and we're going to go up there and check this out. So one of the studies I read was this David Scott Schaefer. This was from his unpublished master's thesis at the University of Tennessee, published in 1984, Late Quaternary, Paleoecologic, Geomorphic, and Paleoclimatic History of Flat Laurel Gap, Blue Ridge Mountains, North Carolina. And he says that the widespread existence of relict, meaning that it's a relic of the past, relict talus, block streams, and block fields, and colluvial fans that date from the late Pleistocene and early Holocene. So we're talking right there in that transition, right there. That's pinpointing us right back to the Younger Dryas era, right? Is evidence of a former severe paraglacial environment characterized by intense freeze-thaw processes in and around Flat Laurel Gap during the full and late glacial. So one of the things about the paraglacial processes is when we're talking about the creation of these boulders originally from what would have been a solid continuous mass of bedrock, that's where we can get into the idea of Mike freeze-thaw. So when you have intense paraglacial, what you're doing is you've got very intense cold, and then that's followed by a seasonal warming, and then intense cold. So you've got this freeze-thaw cycle. That can actually go to work on the bedrock. I still would think, though, that a seismic event is going to be necessary for a full explanation of, I don't think, you see, because of the fact that when we look at the Hickory Run Boulder Field, for example, it's all transported. Paraglacial phenomena, while it can fracture rock, it tends to leave it in the same place, right? So it's still interesting to try to resolve it, and it hasn't been resolved yet. What we're seeing here is just one little regional expression of this evidence that there was something that happened that was another order of magnitude. And the last date that I had up there was putting it right back there in that window. They were using, we'll be coming back to this stuff, but it was talking about thermoluminescence dating, putting it right back to the, to the terminal ice age period. And so what we've been looking at all of these episodes is evidence of fingerprints of some kind of a cosmic event, right? So I want to get to where we kind of have an understanding of both of these things, that yes, there was an event that left this impression in the ice, in the lake deposits, in peat bogs, etc. But then this event had outward manifestations in all of these varied forms. What we just looked at was one of those forms. We just saw evidence that there was something that happened. So the question is, and as Mike saw instantly, we're talking about flushing the valley. We're talking about washing in huge amounts of rock and boulders, depositing it, and then leaving it sit there for 10 or 12 or 15,000 years, whatever, forming the soil over it. So now people go, they build roads, they build their houses on it, trees are growing. Nobody suspects that if you went back in a time machine not that long ago, it would look completely different, right? So what we're trying to do is go, something very unique happened here, right? It left its signature in the landscape in this form that we just looked at. Now, it does appear that at the same time, something else happened. Around large sections of the world, we have deposition of microspherules that only form under high temperature. And we have nanodiamonds, and we have iridium and platinum showing up. We have fullerenes, we have melt glass that's showing up. So the question is how do we connect all of this together? And is there a connection? Would a flood of such outsized scale and magnitude as must have done its handiwork, its geomorphic handiwork in this valley that we were just looking here, the valley of the Pigeon River, was that event connected somehow to the deposition of nanodiamonds and microspherules and melt glass? That's kind of where I want people to be thinking about this.